Hi, today we'll be learning how to derive all the projectile motion equations. Now this should give you a better understanding of how these equations work, where they come from, and you'll have far less memorization to do as a whole. Alright, now before we derive any equations, we have to understand something very important in projectile motion. And that is that we can consider the motion of the projectile in the y direction or the vertical direction and the x direction separately, which means that each of them has their own individual kinematics. So let's label those two axes x and y. Now this might seem quite abstract to you at the moment that we can consider each of these directions separately in terms of their kinematics, but this will become a lot clearer as we derive equations. What this means though is that you can look at each of these individual directions depending on whatever is suitable for what you're trying to find out. Suppose you're trying to find how far this projectile reaches, then you would use the x direction. And if you were trying to find out the maximum height that the projectile gets to, you'd use the y direction. Now, in order to look at each of these directions with their kinematics separately, we can separate this initial velocity vector into its two components. Now let's denote the angle between the velocity vector and the ground as theta. Using simple trigonometry, we can work out that the vertical velocity is v0 sine theta, and the horizontal velocity is v0 cosine theta. And this will become very useful to us as we derive some equations. Now, a final important point about projectile motion is that it is parabolic and symmetrical across a point known as the apex. Or mathematically, you could call it the vertex of the parabola. Now, on to some equations. Now, the first equation we'll be deriving is the equation for flight time. Now, flight time is determined by how long it takes this projectile to go down its path and meet the ground. Now, projectile motion can be considered by its horizontal and vertical components separately, and to determine flight time, all we are concerned about is the vertical position and velocity of the projectile, because, of course, that's what determines its height from the ground. Now, a specific position in the projectile's motion that we want to consider is the apex, and the apex is the top of the projectile's motion. As you can see over here, the velocity at the apex is completely horizontal, and the angle that it makes with the ground, or theta, equals 0 degrees. Now the reason this is because the vertical component of the velocity vector is continuously minimized up to the apex by the acceleration due to gravity. So in essence, at the apex, the vertical velocity is 0, and mathematically speaking, the vertical component of the velocity at any given point in the projectile's motion is equal to the magnitude of the velocity times the sine of the angle that the velocity makes with the horizontal. At the apex, that angle is 0, and we note that the sine of 0 also equals to 0. Therefore, your velocity in the y direction at the apex, which would be mathematically described as the velocity at the apex times the sine of theta, also equates to 0 meters per second. Now, in order to start deriving the equation for the flight time over here, you have to divide the motion into two halves by the apex. Now, the equation we're going to start with is the equation that defines acceleration, which is the change in velocity over the change in time. Now, all we have to do is rearrange this for time, which yields the change in velocity over the acceleration. Now, in terms of the change in time, we are going to be considering the time taken to go from the initial position to the apex, so we'll label that as t apex. Now, in terms of the change in velocity, which is the final velocity minus the initial velocity, we're considering the change in the vertical velocity from the initial position to the apex. At the apex, the vertical velocity is 0, and at the initial position, the vertical velocity is v0 sine theta. Now, in projectile motion, the acceleration is minus g, which is the acceleration due to gravity. Now we simply simplify this, and we get that the time to reach the apex is v0 sine theta over g. Now the thing about projectile motion is that the work done by gravity is equal to 0 because the object lands at the same position relative to the ground, at y equals 0. Now this means that the kinetic energy, or the velocity at the end of its motion, is equivalent to the beginning. Now in projectile motion, our initial velocity in the y direction is minimized by the force of gravity all the way to 0 at the apex, and then as it falls back down, the velocity increases again to its maximum magnitude, just in the opposite direction. Now this can easily be verified because the change in position, or the displacement relative to the ground across its motion, is equal to 0 because it's starting and ending at the surface. This means that the work done by gravity is equal to 0, and that means there is no change in the kinetic energy. So the change in kinetic energy equals to 0 as well. And quite obviously, the time taken to reduce this velocity from its maximum to 0 will be the same amount of time that it takes to maximize the velocity once again. This is because the acceleration due to gravity is constant. Also, the motion of the projectile is symmetrical across the apex. Therefore, the total time taken will simply be equal to 2 times the time that it takes to get to the apex. And this can be rewritten as 2 v0 sine theta over g. And this is our equation derived. Okay, so the second equation we're going to derive is for the range, or how far this projectile goes in terms of the x direction across its path. Now given that we already know that the flight time of the projectile is 2 v0 sine theta over g, deriving this equation is not hard at all. Firstly, we need to establish that there is no force acting in the x direction to change this component of the velocity, because we are assuming that air resistance is negligible. So because our velocity is constant, we can start deriving this equation fairly easily. We start with the definition of velocity, which is the displacement over time, and then we solve for the displacement, which yields the velocity times the time interval. Then we rearrange for position, which yields the velocity times the change in time, and now all we have to do is substitute in the values we know. The change in position in the x direction is equal to the velocity in the x direction, or v0, times the cosine of the angle that the velocity vector makes with the ground, times 2 times v0 times the sine of theta over g, or the flight time. This can then be simplified and rewritten as 2 v0 squared sine theta cosine theta over g. And this is our equation derived. Sometimes, however, you will come across this equation written as v0 squared sine of 2 theta over g. But this is the same equation rewritten because there is a trigonometric identity which states that 2 times the sine of theta times the cosine of theta equals sine of 2 theta. The third equation we'll be deriving is the equation for the maximum height of the projectile. Now we know that the projectile reaches its maximum height at the apex, so our derivation will have to focus on the time interval between the initial position and the apex of the motion. So to start off the derivation, we'll start with a basic kinematic equation which states that the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. Now because we're deriving the equation from the initial position to the apex, our final velocity will be the vertical velocity at the apex, which we know is 0. And the initial velocity will be v0 sine theta. Then as for the acceleration, we know that the vertical acceleration will be the acceleration due to gravity. Then as for the displacement, that will be the maximum height reached, which I will denote as h. Now all we have to do is solve the equation for h. And that is our equation derived.